Okay, so let's talk about the origin of aggregation. Okay, so in order to understand aggregation, we can use this equation that we came up with for the chemical potential of an amphiphile in an aggregate of size n, and that was mu n0 plus kt over n times natural log of an over n. Okay. And so if we wanted to compare the mole fraction, right? So we want to compare the mole fraction of amphiphiles in aggregates of size n to those in aggregates, or those that are monomers. Okay, so how are we going to do that? We would just say, okay, if they're in equilibrium, then we know that mu n0 plus k over n natural log of an over n must equal mu 10 plus kt natural log of a1, right? And so we can sweep the parts that have to do with the bonding onto one side. So we have mu n0 minus mu 10 over kt has to equal natural log of a1 over an over n to the 1 over n. So this can give us an expression for an, so that or for a1. So if we solve for a1, we get that a1 is equal to an over n to the 1 over n power times exponential mu n0 minus mu 1 0 over kt. Okay. Or similarly, we can write down that an over n to the 1 over n is equal to a1 exponential mu 10 minus mu n0 over kt. Okay. So if we want to write down the expression for an, we would get n times a1 exponential mu 10 minus mu n0 over kt to the nth power. Okay. And that should give us the activity coefficient, right? By definition, an is the activity coefficient of n times the mole fraction of n. So now, before we can really say much more, we have to know something about mu 10 and mu n0, right? So we need to know how is the energy of a molecule changing when it's in a monomer versus when it's in an aggregate of size n. So let's just first ask the question, well, what happens if it doesn't, right? What if mu n0 doesn't depend on n, right? So what if mu 10 is equal to mu 20 is equal to mu 30 is equal to mu n0? So it doesn't really matter from an energetic bonding standpoint whether the molecule's in an aggregate of size 1 or an aggregate of size n, right? So in that case, mu 10 minus mu n0 is just 0. So we just get that xn is proportional to n times a1 to the nth power, right? And since we know by definition the activity can't be greater than 1, and n can become very large, we know that xn for large n is going to be much, much less than 1, right? So we know for large n, xn is much, much less than 1. Okay. And we can see that if mu n0 increases with n, that is, if it's higher energy to put molecules in larger aggregates, then the situation gets worse. That is, it gets, right? So then this would get even smaller, right? Because you're going to have a negative number up here. So the thing you're taking to the nth power is even tinier. And so you're less and less likely to have you're likely to have very few large aggregates. But on the other hand, if we were to have a situation where we could lower the energy of the molecules, right? So if we can lower the energy of the molecules by putting them in aggregates, this could sort of mitigate the situation, right? It could help drive to have larger aggregates. Okay. And so we need to look carefully at how do we expect this mu10, mu n0, how do we expect mu n0 to vary with n, right? So the next thing we're going to ask is, how does mu n0 vary with n? Okay.